This problem is an example of a two-point Arrhenius equation type problem. So we have a reaction studied at different temperatures and the rate constants are calculated. We find that the rate doubles when the temperature is increased from 20 degrees C to 60 degrees C, and we want to find the energy of activation, or E sub A. So we know that T1 is equal to 20 degrees Celsius, T2 is equal to 60 degrees Celsius. And for our two-point Arrhenius equation, we have ln of the rate constant 1 over rate constant 2 is equal to E sub A, the activation energy, over R, the gas constant, times 1 over T2 minus 1 over T1. For this equation, our temperatures have to be in Kelvin. So that means that 20 degrees Celsius is 293 Kelvin, 60 degrees Celsius is 333 Kelvin. Our gas constant R is 8.314 joules per mole Kelvin. And we need to know our rate constants. What we do know is that the rate is doubled when the temperature is increased from 20 C to 60 C. And we can just say that the rate constant at K1 is 1, and K2 is double that, or 2. And that'll allow us to solve this problem. So we can set our equation equal to the activation energy. So I'm going to divide both sides by 1 over T2 minus 1 over T1. And multiply both sides by R. That's canceling R on the right-hand side and 1 over T2 minus 1 over T1 on the right-hand side as well. So I'm going to rewrite this to make it look a little prettier. We're going to have natural log of K1 over K2 divided by 1 over T2 minus 1 over T1 times R is equal to E sub A, the activation energy. So we know everything in this side of the equation. We're solving for the activation energy. And again, there are a number of important things to remember. Make sure that T1 and K1 are correlated. T2 and K2 are correlated, meaning we know the rate constant at a given temperature. Those have to be aligned. We need to make sure that our units for the activation energy correspond with those that we use in the problem. So watch your units and then make sure the temperature is in Kelvin. So let's plug in some values. We're going to have natural log of 1 over 2 over 1 over 333 minus 1 over, and that's Kelvin, 293 Kelvin. And then our gas constant is 8.314 joules per mole Kelvin equals our activation energy. If we look at our units, we have 1 over Kelvin, and that's going to cancel with the Kelvin here. So when we subtract these, we're going to be left with 1 over Kelvin, which means our units are going to be in joules per mole for the activation energy. So when you do all of the math here, we're going to have minus 0.693 in the numerator, that's for ln of 1/2, over minus 0.00041 for the subtraction of the two temperatures, times 8.314. Is equal to the activation energy. And I just left the units off in this one. And multiplying this out, we're left with 14053 joules per mole is equal to the activation energy, or 14.05 kilojoules per mole.